Yeah. We're all hurt.
How about blood vessel?
Blood vessels?
Yeah. Torso blood vessel.
Dorsal blood vessel?
I hit send, by the way.
Oh, there it is.
No. No. B.
B. Oh my God, that's a hard one.
I know, right?
What's the clue?
It's
It's the blood vessel
blood-
torso.
It's torso.
Torso blood vessel.
I know what it is.
You.
Why is it not showing?
L.
Yeah.
It's a lovely L. What's the next?
Torso blood vessel.
Why is it not?
A.
Abdominal aorta.
Mm-hmm.
See, it wasn't as hard as soon as you guessed some vowels. I know. All right, what else should we do?
Oh,
What?
brain.
Brain.
Oh, this is good. Good review.
Ooh.
A. A. Frontal. Sometimes you just gotta do the easy ones. Same one. Actually, you know, let's do a skull one. But which skull one? Or a facial gun? Let's do a facial
I
gun.
don't know. This isn't working.
Let's do a facial gun.
Okay.
Oh, it works that way.
M? Yeah. How about an S? Nasal. Oh, did I miss an A?
Yeah.
No, I just put them. No, I did miss an A. I can't spell the A. I'm tired. Oh. No. We only learned some of the ones that had the word nasal in it.
That person may not show up.
You're right, it is 10.
We're not going to discount yet, Grace.
It's a magnet.
Yeah.
Maybe we'll call it.
Oh. All right, it's about that time. Sorry.
Okay.
But I think it's pretty awesome what you were doing. Oh, now I have to remember to turn that on.
You're barely. You don't have to work.
So this is my attempt to record our lecture today. We'll see if it works. As long as it shows up. Okay, not gonna touch it. All right, so let's go ahead and do our attendance. And check our schedule as usual. Okay, is Danielle here today?
Here.
Eric?
Here.
Kirsten?
Yep.
Miranda? Grayson?
Here.
Chelsea? Jason?
Here.
Ryan? Ryan's not here. Macy? Corinne? Jessica?
Here.
Elizabeth?
Here.
Anna? And Jeanette?
Here.
Here. Morgan is here. Olivia? Maisie? Okay. Not too bad. So let's take a look at our schedule and see what we have coming up. For our next week. So today is Wednesday already, thank goodness. So coming up, we have Thanksgiving break on Wednesday next week, so there's no school then. We do have class on Monday, but no quiz. Okay, so nothing until after Thanksgiving break. So just regular lecture. We're getting close to the end. Yes, we are. Okay. So today we are doing the urinary system. If I can get this. Oops. I know, I need to stop meddling. Okay. Oh. The effort I'm going through for this student. Computer does not want to do it. Ooh. There. Got it. I need like a bunch of things to prop this up. It's just not working. It has to do it backwards. Sorry, I shouldn't have touched it. It was perfect.
Did you need to repeat a lot of the questions in the exam?
No, were there a lot of repeats?
Yeah,
Yep, definitely.
There was
Really?
111 questions.
yeah.
I knew there were a lot of questions, but I did not know that it repeated. I even went back through and looked, and I was like, no, they don't look different. I mean, they don't look the same.
I think
Well-
I answered gallbladder like 4 different times.
Yeah.
Oh my gosh. I'm sorry, guys. Good news is there's a drop quiz. I mean, a drop exam.
Yeah, I mean, it's 111 points.
Let's take that one. Let's
Yeah,
drop
we
it
did
there.
really good on that.
You did really good on that one.
Yes.
Okay. All right, so urinary system. This is where we are beginning today. It's not a hugely long chapter, so we might even finish it today as well. This is a great picture.
This was already on the exam.
Yeah, yeah.
It shouldn't have been.
Yeah.
I had a couple of questions about kidneys and stuff.
Well, no, there was the renal artery and the renal vein should have been on the exam.
I think another guy is out there because he thought it was on Zoom. Should I go get him?
Yes.
Because I thought it was on Zoom.
It's
too.
this is because there's someone who's sick today, and I was trying to
Oh, okay.
Zoom for that. No, we're in class. So there are questions on the urinary system. I haven't even written questions on the urinary system.
I have some.
I had a couple of questions about kidneys. It
Okay,
was like blood, it was like blood vessels to the kidneys.
the artery and the vein. More than just the renal artery and renal vein?
I think I had I had the renal artery and renal vein. I had 6 questions just for renal artery and renal vein. They're all the same 6 questions, but.
Okay. Something went wrong. I will take a look at it and see if I can modify.
But we definitely had that picture.
You did?
Yeah.
I don't know what to say about that because
Because that's what picture they used for renal artery and renal vein.
so let's give you guys credit real quick since you were in the other
Yeah, you were
room.
sitting out there for a good 5 minutes.
Oh my goodness.
I'm sorry.
No, it's fine. It's totally fine. So let's give you credit for being here. So Ryan, and then you are
Miranda.
Miranda. Yeah, 2 people who are normally here.
Yeah, I was like, I'm sorry, I saw that Zoom message, I'm like.
No, it was for someone who's sick
I got
and I
confused.
told not to come to class.
Sorry, I got totally confused.
No, that's why I try not to post it until like right before class so that people wouldn't get
Yeah, I
confused.
got it right as I was walking up to the door. I was about to be mad, but then I seen your son sitting there, I'm like, oh, okay, we're good.
Yeah, no, I would not do it
I
to you guys
kept
like
checking
that
it all
late
day long to
notice.
see if
No,
everything-
I would be upset too if I posted it 5 minutes before class started. Okay, well, I will review that exam and see if I can get rid of some of the stuff that doesn't belong.
If we got the questions wrong, you can take those out.
Take out the ones that you got
We should all get
wrong.
100% from this one. Don't take any questions out, just change
If
it.
they're right, you
Just-
can
just change
you can
everybody's
just leave
grade.
the ones that are right. You don't have to take those out.
All right, I'll see what I can do. It probably won't be until this weekend where I can kind of really go through it. But I won't take the ones you got right. But so apparently this picture was used, which is, I don't remember this, but this is a great picture for the urinary system. Okay, so is this one. So anatomy of the urinary system, made up of 2 kidneys, 1 urinary bladder, 2 ureters, and 1 urethra. So the ureters are what carry the formed urine from the kidney down to the urinary bladder. Okay, so kidney location, shape and size. It's shaped like a bean, like a kidney bean. It's about the size of a fist. So this is about the size of a healthy kidney. And you have 2 of those. Kidneys are retroperitoneal, which means they're behind the visceral and parietal peritoneum. And they are partially protected by the rib cage. So if you feel your rib cage, they're kind of up underneath the lower ribs. And the right kidney is actually slightly lower in position of the abdominal cavity than the left kidney. And that's that way with everybody. The right kidney is always a little lower, the left kidney is always a little higher. A good reason why the right kidney is slightly lower is because you have the liver right there as well. So the liver kind of takes up part of that space. So the right kidney is a little lower because of the position of the liver. Okay, there is a layer of connective tissue that surrounds the kidney. This is called the renal capsule. And perirenal fat, which the prefix peri, P-E-R-I, means around. So the fat around the kidney surrounds the kidney and is a shock absorber, helps protect the kidney, helps cushion the kidney against any blows. So this is one place where it's healthy to have fat surrounding your organs. So perirenal fat. Renal fascia, so fascia is connective tissue. And this is connective tissue that surrounds the perirenal fat and helps anchor the kidney to the wall of the abdominal cavity. Okay, then we have the hilum. So let's draw a quick kidney here. So the hilum is this concave region where the renal artery or renal vein enter and the ureter exits. So it's this concave region. Okay. Opens into a cavity inside. And that cavity is called the renal sinus. And this has fat and connective tissue. And this is the area where structures enter and leave the kidney. Okay, so the kidney is first divided into two main regions, the outer cortex and the inner medulla. So, I guess I could have left my picture there. Draw another kidney. So, the cortex is the outer layer. And then we have the inner medulla. Think medulla is the middle, okay? Medulla is the middle. So within the medulla, you have these structures called renal pyramids that kind of have this structure to them. So this would be a renal pyramid. And so these are the cone-shaped regions in the medulla. And we'll talk a little bit more about what they do. Then there's medullary rays that extend into the cortex. And there's a better picture coming up. I'm not going to try to draw it all. And then there are renal columns, which is the same tissue as the cortex, but basically projects between the pyramids. Okay? Then there are renal papillae, which is the little tip of the pyramid. Might as well just see this is our columns. Again, a much better picture is coming up. Okay, then there are structures called the minor calces. And these are basically little chambers that help funnel the formed urine from the renal papillae towards the renal pelvis. The renal pelvis is close to the hilum, where the formed urine collects and then travels down the ureter. So one thing to note is there's minor calces, which are the thin little channels, essentially, that collect that formed urine, that come together into larger channels that are called the major calces. Okay, so this picture here, I know it's a little fuzzy, but it still is a pretty good picture of the anatomy of the kidney. So, looking, first of all, we can see our renal pyramid. And note how the papillae all point in towards the center. Okay, they all point in towards the renal pelvis. So this is opened area. Right before you go down the ureter is the renal pelvis. So the renal papillae empty into the minor calces, the small channels. So this is a good example here of a small channel. Here's another small minor calces. Those empty into larger channels which would be a major calcium, which then empty into the renal sinus. I'll see if I can find you guys a better picture that's not fuzzy. This picture has just been blown up so much so that you can see stuff that it has gotten a little fuzzy. I am not going to ask you about all of the different arteries and veins of the kidney. You do need to know the main one, like the renal vein and the renal artery. But all the little tiny ones, I'm not going to ask you about, but I will ask you about all of the anatomy, all the structures of the kidney itself. So note, cortex is the outer layer where you do not find the renal pyramids. The medulla is the inner layer. Medulla means middle, not really, but it's a good one to remember. So in the medulla is where you find your renal pyramids. Your columns are in between your pyramids. And then you have your fibrous capsule, which is fibrous connective tissue, which is pretty tough and it helps hold that organ together. See if I'm missing anything here. Okay, I think we've touched on everything. One thing to note, just take a second and appreciate the blood supply to the kidney itself. Because what is your kidney doing? It's filtering your blood. So you need a good blood supply. That renal artery is bringing in blood to be cleaned, essentially. Get rid of that extra urea, get rid of extra proteins and ions, etc., that you do not need in your blood supply. So you have a good blood supply to the kidney so that you can clean that blood. Okay, internal anatomy, the nephron. So the nephron is the histological and functional unit of the kidney. So if I ask you what is the functional unit of the kidney, it's the nephron. And the nephron is a small tubulous structure, but this is where on a singular level, the cleaning of the blood actually occurs, filtering the blood. Okay, so this is a tube-like structure. It has an enlarged end called the Bowman's capsule or glomerular capsule. Either one, same thing. So that would be this structure right here, and there's a better picture coming up. So an enlarged end with a capsule, a proximal convoluted tubule, which means it's going to be all folded and twisted, a loop of Henle, the distal convoluted tubule, and then that leads into a collecting duct. So these are the structures that make up the nephron. So you will need to know those major structures. Fortunately for you, you're not in physiology, most of you, and some of you are.
No, I was twice, and that's no fun. It's a lot of fun.
In physiology, you get to learn all about how urine is formed and the filtration process occurs. And that is, oh, I know the two ladies over there, and you too.
No, I just got a message from Chelsea that said to let you know that she can't get in the middle.
You can't get, oh, let me see. Oh, there's two people waiting. Okay, let her know I just admitted them. That should do it. Okay, she's in now. Okay, thank you. Okay, so we're not going to do physiology of the kidney in this class. So you're welcome. Okay, so distal convoluted tubule, which is the last part of the nephron, empties into the collecting duct. And that merges into the papillary duct, which empties into a minor calyx. And which will then eventually empty into a major calyx, then to the renal pelvis. Okay. All these structures of the nephron are found in the renal medulla. So there are quite a few, over 1.3 million nephrons in each kidney, and they measure between 50 to 55 millimeters in length. So that's about this long for each nephron. And so they're very thin, and then they're folded up quite a bit. So they take up very little space. There are juxtamedullary nephrons, which lie near the medulla, so near the center. And these have long loops of Henle, and these have loops of Henle that extend very deep into the medulla. And there's only about 15% are juxtamedullary nephrons. The rest are just regular nephrons, or cortical nephrons. So a cortical nephron does not have a loop of Henle and extend into the medulla. So let's really quick, I'm going to draw a nephron. So we have a Bowman's capsule. If I could spell. Bowman's capsule. Then you have this kind of twisty proximal convoluted tubule, or PCT, okay? Then that dips down and comes back up. Where it dips down and comes back up, this is the loop of Henle. Then, when it gets back up to the up again, it starts bending and twisting. And this is your distal convoluted tubule. And then it empties into a collecting duct. So those are your major regions, your Bowman's capsule or your glomerular capsule. Proximal convoluted tubule, so proximal because it's proximal, it's closest to the beginning of the nephron, the loop of Henle that loops down, then the distal convoluted tubule, and then it empties into the collecting duct. Okay. So here, this picture here is showing you the difference between a juxtamedullary nephron and a cortical nephron. So the juxtamedullary nephron is the kind that has loops of Henle that dip in quite deep into the medulla, into the renal medulla. Okay? Cortical nephrons do not dip down so far into the medulla. And so remember, there's about 15% of juxtamedullary nephrons, and then the remaining 85% are the cortical nephrons. Many nephrons will share a single collecting duct. That's pretty normal. And then that collecting duct ends at the tip of the renal papilla. Okay, so the renal corpuscle. The renal corpuscle is made up of the Bowman's capsule and capillaries that are surrounding it. So you have your Bowman's capsule, and then you have capillaries that are all surrounding it. Okay, this is where the blood is being filtered, and that filtrate enters into the capsule from the blood. So the Bowman's capsule, the outer layer is the parietal layer. This is made of this is made of simple squamous epithelium, and it becomes cone-shaped at the beginning of the convoluted tubule. So the convoluted tubule here, and carries away from the Bowman's capsule. So the layer of cells that makes up the Bowman's capsule is one cell layer thick, simple squamous epithelial cells, and then it's surrounded by blood vessels. So this is setting it up for a great way for filtration to occur from the blood into the capsule. Okay. Then there is the visceral layer, which is the inner layer, and this is made up of special cells called podocytes. And these podocyte cells wrap themselves around the capillaries that are surrounding the Bowman's capsule. And they wrap themselves around, and it's almost like they have little fingers that wrap around, and you end up with these little slits in between the fingers, essentially. And this is where the filtrate is able to pass through into the Bowman's capsule, but keeps in the blood all of the blood cells, for example, and larger material that shouldn't be filtered out in your urine. Okay, fenestrae. These are endothelial cells of the glomerular capillaries, and I have a really good picture coming up of this. So the filtration slits is what I was kind of talking about just then. These are those gaps between the podocyte processes, and this is where the filtrate from the blood passes into the glomerulus, where the whole process of filtration can occur. So the filtration membrane is made up of capillary endothelium. So remember, capillary endothelial cells, those are simple squamous epithelial cells, one cell thick. The basement membrane, and then those podocyte cells. So the first step of urine filtration begins when fluid from the glomerular capillaries filters across the filtration membrane and into the Bowman's capsule. So here is a great picture, hint, hint, but this is a good picture, kind of showing you much better than I can draw what's going on inside the Bowman's capsule. Okay, so first of all, our capsule, our glomerular capsule, our parietal layer is simple squamous epithelial cells, so one cell layer thick. And then inside is just like a knot of capillaries. And those capillaries are surrounded by podocytes. And those podocytes wrap around the capillaries and kind of do that, have those extensions kind of wrap around each other until you have these filtration slits. And so the fluid from the blood passes out from the capillaries, so fluid, dissolved substances, anything that's small enough to pass through these filtration slits will enter into the Bowman's capsule. Otherwise, anything that's larger, like cells or proteins or other molecules, they're gonna stay in the capillaries because they cannot pass through those filtration slits. Make sure I've got everything here. Okay, so once that fluid has passed through the filtration slits, it enters into the proximal convoluted tubule. So that's where it begins its whole journey of urine formation. But this is a great picture, kind of showing you what's going on in that corpuscle. Okay. You have two arterioles. You have an afferent arteriole, which supplies blood to the glomerulus, and an efferent arteriole, which drains blood away from the glomerulus. So if we back up real quick, our afferent arteriole brings blood into the glomerulus. The efferent arteriole drains blood away. Okay? Okay. There is a layer of smooth muscle that lines both the afferent and efferent arteriole, and that controls the flow of blood to and from the glomerulus, which ultimately helps control the rate of filtration formation. The macula densa is a specialized tubule, and it's made of cells in the distal convoluted tubule, and that's found next to the renal corpuscle. So back up again. Macula densa is these specialized cells that are right up next to your afferent arteriole. These are the macula densa. And note that the macula densa is part of the distal convoluted tubule. Okay, then the juxtaglomerular apparatus. These are juxtaglomerular cells, so cells up next to the afferent arteriole and the macula densa. And the role of the juxtaglomerular apparatus is it secretes enzymes that control the rate of filtration formation and regulate blood pressure. So I'm not going to go into hormones and blood pressure and all that stuff. That's physiology. But you should know just this line here of what's going on at the juxtaglomerular apparatus, okay? Okay, proximal convoluted tubule is about 14 millimeters long, so about the width of your finger, maybe. Not very long. And it's made up of simple cuboidal epithelium. So this is different than the cells of the Bowman's capsule, which is simple squamous epithelium. These are simple cuboidal epithelium, which means it's going to be harder for things to diffuse across. So it's more impermeable. And in addition to it being cuboidal, there are microvilli attached to the apical surface. So you have your basement membrane where the cells are attached. There's your nuclei. And then, so this would be your proximal convoluted tubule. this is what it would look like inside the proximal convoluted tubule. That filtration or that filtrate that just formed is going to pass down this lumen, this hollow portion, and come in contact with the microvilli of those cells. Okay, so right here it shows you the beginning of the proximal convoluted tubule, and you can see the little microvilli. These are simple cuboidal, whereas remember the capsule are simple squamous. So different cell types, different functions. Okay, looking at the loop of Henle, this is a continuous tube. It's continuous with the proximal convoluted tubule and with the distal convoluted tubule. But there are some structural differences in the tube itself, depending on where it's found. So the proximal convoluted tubule is closest to the Bowen's capsule. The loop of Henle, you have a descending loop of Henle and an ascending loop of Henle. Okay, so the loops that extend into the medulla, like the juxtaglomerular nephrons, they become really thin near the ends of the loops. So the cells actually change. So they switch from being simple cuboidal higher up to simple squamous down at the bottom of the loop. And then when you go back up the loop of Henle, they switch back to simple cuboidal again. And then you have your distal convoluted tubule. And your distal convoluted tubule is not as long as the proximal convoluted tubule. And so one thing that makes the distal convoluted tubule different than the proximal convoluted tubule is there's not as much microvilli. So I was drawing a cell from the distal convoluted tubule. Maybe there's a few microvilli, but not very much. So that's one of the big differences. And then, as I mentioned before, many tubules will connect to the same collecting duct. They share collecting ducts. Okay. Polycystic kidney disease. This is a disease where kidneys become enlarged, often with fluid-filled cysts, and they can become quite enlarged. So remember, about the size of your fist is a healthy kidney for your body. And note in this picture, this is a person's hand. And the other person, the other hand. So these kidneys are grossly enlarged. And that is one of the causes of kidney failure is polycystic kidney disease. So the cysts will increase in number as the person ages. And this can, as I mentioned before, can lead to kidney failure and is one of the reasons the person with polycystic kidney disease would need a kidney transplant. So third leading cause of renal failure. What do you think are other causes of renal failure? That's liver failure. But yeah.
Medication.
Hmm?
Medication overload.
Oh, medication overload. Yes. Diabetes is a big one too. So some things can be prevented. Polycystic kidney disease is something that cannot be prevented. It's a disease that a person has. Okay, so if a person has polycystic kidney disease, 50% of the people will need dialysis. And of those people, many will also need a transplant. Okay, arteries and veins of the kidney. So this is what you do need to know for the arteries and veins. Okay, knowing the correct flow of blood through the kidney. Okay, so this is right here for you. So from the renal artery to the segmental artery to the interlobar artery, arcuate artery, interlobar. Did I do that twice? I did. Interlobar artery, afferent arterial, glomerulus, afferent arterial. So right here, we've already talked about these guys. Peritubular capillaries is where you actually have exchange occurring in the capillaries. The vasa recta, which is a small vein, interlobar vein, arcuate vein, interlobar vein again. So I don't think we did it wrong. And renal vein. Back, let me check my trusty book real quick. Oh, it's gonna have the. Okay, it is in there. Segmental artery, interlobar artery, arcuate artery. Actually skipped one there. Cortical radiate artery, afferent arterial. So perhaps this one, I already forgot the name of it. Cortical radiate artery. That's the one thing I got wrong. I put interlobar twice. This is in your homework, so it is listed out for you. And I would give you the page number, but I know you guys don't have page numbers on the online book. But it looks like this on the list. Okay. Okay, so this is another great picture. It's not pixelated like the other one was. And it shows you a little bit better the blood supply, but also you're able to see really well the vena papilla emptying into minor calyces. Then those minor calyces join together to form major calyces. But this picture is specialized for looking at the blood supply. I promised you already that I wasn't going to have you identify all of the different vessels in the kidney, so I'm going to keep my promise. You do need to know the major ones, and you do need to know the basic order here. But I won't make you identify them in a picture. This is a good picture here, though, because it does show you one single renal pyramid, how it comes together to the minor calyx. And so one renal pyramid is made up of many nephrons, and their collecting ducts all come down to that point at the renal papilla. So this is in the medulla. Here's the cortex. Oh, I'm gonna go through this. I'm skipping these. Okay, urine production. So remembering that nephrons are the functional units of kidneys, and these are the smallest components that are capable of producing urine. So one little nephron can produce urine. It's the collective job of all of the nephrons in your kidney that produces the urine that you produce. Okay, 3 major processes that are essential for urine formation. The first is filtration. And this is the movement of water and small solutes like ions, for example, across a filtration membrane. So the fluid that enters the nephron is called filtrate. So at that renal corpuscle, when the fluid passes through the glomerulus, through the filtration slits, it becomes filtrate. So it's basically the plasma and things that are dissolved in the plasma when they enter into the corpuscle become filtrate. Okay, the second major process that occurs is tubular reabsorption. And this is where you have the movement of water and solutes from the filtrate move back into the blood. So not everything that moves into the proximal convoluted tubule stays there. A lot of it is reabsorbed back into the bloodstream. Okay, then the third step is tubular secretion, and this happens through active transport. And this happens across the wall of the nephron using energy. So urine, this is our calculation for urine, our little math problem. Urine equals the substances filtered across the filtration membrane, substances secreted from the peritubular capillaries into the nephron, minus the substances that are reabsorbed. Okay, so this is a great picture because it shows you the 3 major steps. Okay, your glomerular filtration, where you form your filtrate. And that filtrate, basically a plasma and substances dissolved in plasma that are able to pass through that filtration membrane, enter into the proximal convoluted tubule where tubular reabsorption occurs. So a lot of the ions and a lot of the water is reabsorbed. And you down your epithelium, up your epithelium, and the distal convoluted tubule is where tubular secretion occurs. Tubular secretion is active, so you're using energy to secrete substances into that distal convoluted tubule, stuff you want to get out of the bloodstream as waste. And then that connects to a collecting duct. And a lot of reabsorption of water occurs along the way in many places. So water is reabsorbed during tubular reabsorption in the proximal convoluted tubule, happens in the leukopenly, and also happens in the collecting duct. Okay, a little bit more about the filtration membrane. So the filtration membrane is made up of podocyte cells, and they prevent blood cells and proteins, larger substances from moving from those capillaries into the glomerular capsule. So this is just a drawing, but it's a pretty good one because it shows you the podocyte cells, these are the nuclei of the cells, and how they form these little slits where just the fluid is going to be able to pass through and the dissolved ions, but nothing big. Okay, any proteins that are able to pass through this membrane is going to be actively reabsorbed, because finding protein in urine is actually a sign that something is wrong, that something is not working right. Just the same as if you're finding blood in your urine, that's also an indicator that something is wrong. Okay. Filtration pressure, just a definition for you. We're not calculating this or anything. There is a pressure gradient for which forming the filtrate depends on. So fluid from the glomerular capillaries, forces fluid from the glomerular capillaries across the filtration membrane into the Bowman's capsule. So just knowing that there is this filtration pressure that's forcing this fluid through. And this is due to the afferent arteriole bringing blood, which also has pressure because it's an arteriole, and that helps force the fluid across. This picture is something you'd have to learn in physiology, but for our purposes, just a little bit of appreciation of first the anatomy of a nephron. So here's our glomerular capsule, our proximal convoluted tubule, our loop of Henle, our distal convoluted tubule, and then our collecting duct. One thing of note is look at all the places where water is being reabsorbed. So there's a lot of there is a lot of water reabsorption occurring. In fact, a lot of the substances that filter out in the Bowman's capsule get taken back into the blood. So very few things actually end up staying in your formed urine. So that's all, we're not going to go into that one. Okay, tubular secretion. Okay, so tubular secretion involves movement of substances into the nephron. So secretion can be active or passive. So for example, ammonia will diffuse into the nephron passively. Hydrogen ions, potassium ions, penicillin, para-aminohippuric acid are actively secreted. In fact, hydrogen ions and sodium ions play a really important role in the formation of urine, especially sodium ions. Okay, how do you concentrate urine? So when large volumes of water are consumed, so you drink lots of water today because that's the healthy thing to do, your body needs to get rid of that excess water. Because if you keep that excess water, that's going to build up your blood volume levels, which is going to increase your heart rate, increase your blood pressure, which is not good for you. So your body wants to get rid of that excess fluid. And you want to do it without getting rid of those electrolytes. those dissolved ions. You want to keep those. So the kidneys is what is responsible for doing the job, getting rid of that excess fluid and retaining those electrolytes. In addition to that, when you do not consume enough water, let's say maybe you drank a lot of coffee today and didn't drink enough water, the kidneys are going to produce smaller amounts of urine that is more concentrated as a way to conserve your fluid, helping to conserve water. Okay, there is a concentration gradient across the medulla. So the kidney's ability to concentrate urine depends on maintaining a high concentration of solutes in the medulla. So you have a concentration difference across the kidney itself. So moving from the cortical region to the medulla, the interstitial fluid, the fluid in between the cells, becomes more and more concentrated the further in or the further towards the medulla you go. When you get to the vena papilla, it's highly concentrated compared to the cortex, which is less concentrated. So at the vena papilla, it's even more concentrated than seawater. If you've ever been to the ocean and accidentally swallowed some water, you know that's pretty concentrated stuff. So your kidneys have a really good ability to concentrate this interstitial fluid, which helps in the formation of concentrated urine. So maintaining this high solute concentration difference depends on the function of the loops of Henle, the vasa recta, and the distribution of urea. Because not all urea is going to be excreted. Some of it's kept and held in the kidney to help maintain that concentration difference. Okay. Major mechanisms that create and maintain high solute concentration in the medulla. Active transport. Oh, this is one slide of a tiny bit of physiology, forgive me. Okay, so major mechanisms that help maintain a high concentration of solutes in the medulla. Active transport of sodium ions and symport. So symport means if you're transporting sodium, potassium's coming along too, just coming along for the ride. And symport of potassium and chloride and other ions in that thick portion of the loop of Henle. Another mechanism that's important is the impermeability of the thick and thin segments of the ascending loop of Henle to water. The vasa recta, this supplies blood to the medulla and removes excess water and solutes. An active transport of ions from collecting ducts into the interstitial fluid of the medulla. So you're not reabsorbing it back into the bloodstream, but you are dumping it into the interstitial fluid surrounding the nephron, building up that concentration outside the nephron, which builds up that concentration difference in the medulla, which plays a really important role in how you're able to concentrate urine. Okay, and then urea cycling, which you really don't need to worry too much about this, other than that it happens. Okay, You guys are doing so good. Let me see how much more we have to go. We have a little bit. Okay, we'll go a little bit longer, then we'll finish this up on Monday. Okay, so regulation of urine and concentration and volume. Okay, so regulation maintains extracellular fluid, osmolarity, and volume. So regulation is maintaining these three important factors. Filtrate reabsorption. So remember, filtrate is what has basically left the afferent arteriole and entered into the Bowman's capsule. So the plasma and the dissolved ions, that's your filtrate. So filtrate reabsorption in the proximal convoluted tubule and descending loop of Henle is going to remain constant. Reabsorption in the distal convoluted tubule and the collecting duct is what is regulated. And it's regulated by hormones, autoregulation, so by the nervous system and the sympathetic nervous system. This regulation can depend on whether you've had excess water. So if you have dilute filtrate that's passing through the distal convoluted tubule and into the collecting ducts, you're not going to have much change in concentration. That is going to trigger this process. If you need to conserve water, water is reabsorbed, producing very concentrated urine. So if you drink a lot that day, you're probably going to urinate a lot that day to get rid of that excess fluid. But if you didn't drink very much that day, you're going to find that you're having to urinate very infrequently because your body's trying to hold on to that fluid. And whatever you do urinate is going to be more concentrated than normal. Okay, two major mechanisms. Oh, I thought I deleted this. Okay, all you know is just this one slide, okay? There's two major mechanisms for water balance. The renin-angiotensin-aldosterone mechanism, which is sensitive to changes in blood pressure, and the antidiuretic hormone, which is sensitive to changes in blood osmolarity. So whether it's become more or less concentrated. So each of these two mechanisms is activated by different stimuli. Oh, let me double check this. Oh, okay, we're good. I was freaking out that I put too much in there for you. Okay, antidiuretic hormone. A lack of antidiuretic hormone will result in an increase of urine production. Okay? This can result in diabetes insipidus. Diabetes refers to producing large amounts of urine. Insipidus refers to the production of clear, tasteless urine. So tasteless. Yes, it was a thing back in the day before we had ways to test people's blood and urine, is that doctors would actually taste the urine of their patient to see if it had a sweet flavor to it or not. Because that was one way to diagnose a diabetic. Diabetes mellitus produces large volumes of urine with high concentrations of glucose. So mellitus means honeyed or sweet. So again, that is how they were, I had to put this in there. How people were diagnosed back in the 1800s or earlier was the doctor had to taste their urine to find out whether or not did it have a sweet taste to it or was it not sweet? It was a way to diagnose diabetes. Okay, so we're going to stop with that. We're going to start again on Monday with formation of concentrated urine. And we'll finish up this chapter and get into, I think our next chapter is reproductive system. I'm pretty sure. And no quiz this week, so you guys are good for that. Have a fantastic weekend, and I will take a look at that exam and see what I can do.
Also look at number 61, make sure that one's wrong.
61.
Mhm.